We've all been there, right? You're right in the middle of a super important video call, and boom, everything just freezes. Or maybe you're playing an incredibly intense online game, and your character glitches out at literally the worst possible second. It is honestly just a really frustrating part of modern life. Well, welcome to this explainer. Today, we're going to explore the technology that's actively solving this massive headache. We're talking about Starlink. And we're going to skip all the corporate fluff and jump right into the actual hardware and orbital mechanics driving this whole low Earth orbit revolution. Okay, let's dive right into this. But before we get into the cool spaceship stuff, we need to clearly define the ultimate enemy of our digital lives: latency. Latency is, quite simply, the round-trip data time between you, the user, and the satellite up in space. It's the delay. And when that latency is high data rate activities, like streaming movies, hopping on a video call, or playing competitive games, they basically become impossible to enjoy. So that begs the question, why is traditional satellite latency so high? I mean, if we've had satellite internet for decades, why is it only just now getting fast enough to actually handle our modern needs? Well, to understand this shift, we kind of have to look at the physical limitations that completely plagued the older tech. And spoiler alert, it all comes down to a massive distance problem. Section 1. Beating the distance problem. And here is where we meet the historical villain of our story, geostationary orbit. For a really long time, this was the absolute gold standard for internet from space. But it comes with this built-in delay that physics just won't let us ignore. Let's put this into perspective with a simple analogy. Think of your data as a commuter just trying to get to work. Most traditional satellite internet relies on single geostationary satellites parked way, way out there, like 35,786 kilometers away from the planet. That is one brutal daily commute for your data. But Starlink operates in low Earth orbit, or LEO, hovering right around 550 kilometers above us. So instead of this agonizing cross-country road trip, your data's commute is basically just a quick hop across town. And because these Starlink satellites are orbiting so much closer to Earth, that latency just drops off a cliff. We're looking at a blistering 25 milliseconds for Starlink, compared to a sluggish 600+ milliseconds for those older single satellites. That massive, unbelievable reduction is the exact reason why you can finally jump on a video chat or game over a satellite connection without wanting to pull your hair out over the lag. Section 2. Anatomy of a Starlink satellite. Okay, now that we've got the orbit figured out, let's shift gears from orbital physics to the cutting-edge aerospace engineering actually packed inside these spacecraft. Let's kind of zoom in on the specific hardware here. To deliver all that data, each of these satellites is absolutely loaded. First off, you've got 5 Ku-band phased array antennas and 3 dual-band antennas just blasting high-bandwidth connectivity down to us on the ground. But to point those antennas with pinpoint accuracy, the satellite uses these custom-built star trackers. These are incredible navigation sensors that literally survey the stars around them to figure out exactly where the satellite is and how it's oriented. It's like celestial navigation on steroids. And finally, 4 reaction wheels give it this agile control. They run in a hot spare configuration, so they're super reliable, and get this, their aluminum flywheels are fully demisable, meaning at the end of their life, they just safely burn right up in the atmosphere. Now, a truly massive innovation here is the propulsion system. Starlink is actually the first ever spacecraft flown in space to use efficient argon thrusters. And this matters tremendously, right? Because these thrusters are what allow the satellite to raise its orbit after launch, maneuver around up there to dodge space debris, and, like we just talked about, safely deorbit itself when it's done. It's a really huge step forward for keeping low Earth orbit sustainable. Of course, running all this tech requires a whole lot of power, so Starlink uses a dual solar array paired up with a high-capacity battery. But notice the specific engineering choice here. These solar arrays are aero-neutral. That means their shape won't cause drag or slow the satellite down, which allows for much faster on-orbit maneuvers. So for you and me, having this continuous power, combined with that agile movement, means one thing: a totally stable, uninterrupted Netflix binge. Section 3. Space lasers and the internet mesh. Now, we've talked about how they talk to Earth and how they move around, but the absolute sci-fi magic of this whole system happens when we look at how these thousands of satellites talk to each other. They don't just beam data up and down. No way. They talk sideways, straight across the vacuum of space. Each Starlink satellite has 3 optical space lasers on board. Operating at these insane speeds of up to 200 gigabits per second, these lasers form this gigantic, invisible global internet mesh. It basically allows data to just zip around the globe from satellite to satellite at the speed of light. It's wild. And what's really cool is that this technology is actively expanding outside the main Starlink fleet. Engineers have actually developed these Starlink mini lasers that are designed to be retrofitted onto other manufacturers' spacecraft. They can hit link speeds of 25 gigabits per second in low Earth orbit, which gives those other systems immediate data delivery and real-time command and control right from the ground. It's effectively taking this high-speed space mesh and hooking up entirely different vehicles to it, which completely changes the game for off-world networks. Section 4. Building the Global Constellation. Now, you might be wondering, how do you even pull this off? A network like this doesn't just magically appear out of thin air. It takes a crazy strategic advantage on the ground to actually build, launch, and maintain this massive web. The satellites themselves are engineered in Redmond, Washington, while the customer kits are made in Bastrop, Texas. Each satellite uses this super compact, flat panel design. This minimizes the volume so they can pack a really dense stack of them into SpaceX's Falcon 9 rockets. And because SpaceX is the world's leading launch provider, they're the only satellite operator out there that can just launch its own tech whenever it needs to. This creates this incredible feedback loop of frequent, low-cost launches, meaning the constellation is just constantly getting upgraded with the absolute latest tech. So that leaves us with a pretty massive question. If low orbit creates a constantly upgrading global mesh that entirely solves the latency problems of the past, what terrestrial limitations are we going to conquer next? I mean, it is just incredible to think that the solution to our everyday frustrations, like laggy video calls and freezing games, is literally thousands of argon-propelled, laser-beaming satellites zooming 550 kilometers above our heads. It really forces us to wonder just how seamlessly connected our future is going to be. Thanks so much for joining me for this explainer. I hope you found it as fascinating as I did, and I will see you in the next one.